So I just wanted to say in starting that one of the main things here that we're covering, electricity, some things in electricity are factual, and some things are opinion, especially when we start talking about the NEC. So, we want this to be kind of a discussion thing at times. We have presentations, but we want everybody to ask all the questions they can have, because as many times as we've talked about NEC here, every single conversation, something new comes to mind. And because it's so vague, you get to choose things. And so what we're saying here is that whatever you guys take away from this, if you get an inspector, code enforcement officer comes in, you want to be able to defend what you've done. Here's why I fused this the way I did. Here's why I used this size wire. And that's what this event is kind of about, is learning about what to do with that. And of course, you have to understand some basic electricity, so that's what we're starting with. So that's the end of my housekeeping list. So I'll introduce Richard Houghten.
Thank you. Thanks, Rick. It's an incredible amount of work that goes into planning something like this. And I think we're only seeing the tip of the iceberg here. What I'm going to do is basically 3 sections. The first will be a PowerPoint presentation on basic electricity that has been loaned to us by the folks at SSOS. It's written more from an engineer's viewpoint than it is from an organ builder's. You sort of have to distill it, and like tossing a salad to get to the good stuff. Then the next section will be a presentation I do every year before the AIO convention. It's supposed to be an exam review, and it goes through basic electricity with some actual applications to organ building. And then probably after the break, there's a contraption here that I reacquainted myself with yesterday, where we plug in big, beautiful parts. And I did this once at a convention in Tennessee, I think, and went all out. I had a little smoke maker behind it. And see what happens when you put the diode in the wrong way. Sadly, that's not going to happen today. So, I've put together some pictures at the back, sort of the good, the bad, the ugly, and I see one of them is upside down already. Yeah, well, anyway, you can glance at that. And there are an assortment of stuff on the bench there. There's some meters. You asked me to talk about meters. Mm-hmm. So we'll pass those around. There's a beautiful vintage meter there. Don't drop it on your foot, you'll break your toe, and there'll be another person hobbling around here. And I've circulated a document that was produced in Germany during the past year on standards for wiring in organ building. And there it is. Okay. Voltage is the driving force in a circuit. It's sometimes easier to think about it as pressure in a water system. In a perfectly designed system, the pressure at any point is always the same regardless of the situation. We know this is not always achieved, but the same principles apply to electricity. Pressure is always highest when there is no flow. The guy standing here has a perfectly stable pressure situation. The faucet is off, and the pressure is the same everywhere in the pipe. In fact, the pressure is determined by the height of the water in the tower. You're so intuitive. When the faucet is turned on, water will flow. The pressure of the water in the tower forces water out of the faucet. What influences how fast the water fills the bucket? Okay, let's add. What influences the fact? How fast is the water going to fill the bucket? What factors influence it? Restriction?
How long the pipe is?
How long the pipe is? Are you reading the notes?
No. Just like it water's in the tank.
How much water's in the tank? How high that water in the tank is? So, next, maybe it'll put them up here. Yes. Okay. Look at that. Isn't that amazing? I can just sit here. No. roughness of the inside of the pipe. That's a factor. Okay, next. How does this relate to electricity? The water pressure is measured in pounds per square inch, is the voltage of the power source measured in volts. Next. The how much the faucet is open relates to how much a transistor, which is an electric valve, is open. See, that's the engineering part of this coming out. The diameter of the pipe is the same as the diameter of the wire, the cross section. The roughness of the pipe is related to the resistance of the material the wire is made of. Copper is traditional. We've been seeing in recent years some aluminum wire for house wiring, and certainly those big cross-country transmission lines are aluminum. The length of the wire is similar to the length of the pipe. Next. Oh, I don't have that one. Oh, yes, I do. Okay, here, we can go. The higher the pressure, the greater the flow. That's obvious in a plumbing example. It's certainly the same thing with electricity. The more volts you have, the more current's going to go through. The lower the restrictions, the more the flow. If you have a teeny tiny wire and you're trying to shove a bucket load of electrons through it, there's going to be a restriction. A big fat wire passes right on through. Yes, pretty much what I said. Next. So, it says here, now for some math. The translation of these hydraulic principles into a mathematical formula is the natural progression of this concept. There is only one formula you need to know. Actually, there are two, but we'll get to that. And it's called Ohm's law. Next. Yes. Ohm's law says that the current is equal to the voltage in a circuit divided by its resistance. So, if you double the voltage, you double the current. Has everyone taken algebra? Okay. I had a wonderful algebra teacher. Her name was Iva Hooper. And she was a spinster, and her sister taught geography or American history or something. And Iva always encouraged us, she held up stick-to-itivity as a model for our behavior. And she used as an example Tom Sawyer, who stuck to whitewashing that fence. I realize now it was tongue-in-cheek, but I thought at the time that she's very confused. Okay, next. She would have approved of several ways that we'll get to of rewriting Ohm's law. So, there is a convention that electronics professionals observe, and that is that current is said to flow from positive to negative. They always create circuits that operate in this way. It may not seem like it when your experience in organ building has the common either positive or negative. Next. Yes. Circuits are depicted with a number of symbols that are part of an international language. These are known as schematics or circuit diagrams. There are also a number of important conventions used when circuits are drawn. Generally, the flow of information through a diagram is from left to right, wherever possible. I suppose in countries where they write backwards, or I have this amazing Arabic typewriter, it types backwards, but that's a diversion. We go from left to right, top to bottom. The power feed is at the top, and the ground reference is at the bottom. Here's the same circuit, but drawn using a ground symbol to simplify the drawing. When there are many circuits to be drawn, this removes confusing lines from the diagram. It also shows the importance of a ground reference in the mind of the designer. Ground is the reference point in a circuit and has a voltage potential of 0 volts. We're used to talking about plus and minus. And, if we're questioned, maybe we realize minus is 0 volts and plus is 12, 14, 24, 1,000. But if you work in the phone company, you still have 0, but everything works negative, and it's negative 48 volts. The term ground comes from the AC power distribution people. This type of ground is used to reference AC circuits. The potential of earth beneath us is more commonly called earth ground. It's vital for electrical safety and lightning protection. Chassis ground is used to provide a link for safety precaution to earth ground. Chassis ground is the most commonly used symbol in schematics and refers to the ground reference for the circuit. Circuit ground may use one of the symbols here, or it may just be a simple oblique line as in the previous slide. At this point, you may be asking yourself why so much of this text has been devoted to grounding. This is because it's the single biggest source of misunderstanding when finding fault and measuring circuits. Developing a real understanding of this concept will help to avoid many of the pitfalls ahead of you. Not all, though. Looking in detail at a blurry power supply, we can see 3 terminals, 2 for power and 1 for chassis ground. In this case, the chassis ground is actually fixed to the case of the unit. For safety reasons, the chassis ground will be connected to AC earth ground via the AC cord. It's not necessary to connect the chassis ground to the organ, as there are no dangerous voltages. In this case, the negative terminal is the circuit ground. All voltages in the system are referred to this 0-volt ground. Many of you may be aware that it's been advised by some solid-state manufacturers to clip the wire inside Astron power supplies that links its negative terminal to earth. How many people do this or know about it? Yeah, of course. I like to explain to people, well, you don't want your organ negative floating all over the building, do you? Oh, no. Anyway, it's been known to cause problems because it develops a separate ground bus within the organ apart from whatever you may have installed. I was asked a few years ago to go look at it was a Laterno organ actually, in Grand Rapids, Michigan, where someone had changed the power supply and the organ was behaving very, very poorly. So I'm driving there and just like little Jimmy, I'm thinking, ground wire, all the way to Grand Rapids. But no, in fact, they had multiple power supplies throughout the organ, and they had not put in a common ground wire between them. The only reason it worked was because of the third prong on the AC cord and the fact that they hadn't opened the Astron up and cut the black wire that connects negative to chassis. So the local technician put in a supply that looks a lot like that one, which doesn't have its negative connected to earth. And well, I said, oh, the organ's going nuts. Well, it was. It was a simple fix. Resistance. Very good. From Ohm's law, we can see that if the voltage in a circuit is fixed, then the resistance affects the amount of current that goes through the circuit. First, some math. It says here, I'm going to assume that the power supply is set to 15 volts, so we can have some real-world examples, even though it makes the math a bit tougher. If we connect a 40-ohm coil to the circuit, what will the current be through it?
In here next.
There we go. Next. Okay, Ohm's law. This is real easy. So the current is equal to the voltage, 15 volts, divided by the resistance, 40, and the answer is 0.375 amps. In the next section, we'll get to what volts and amps and watts are, but just accept it for now. What would the current be if there were 2 coils? two 90 ohm coils? Well, you all know the answer. It would be twice. Question is, are they in series or parallel? This is an engineering question. We don't generally use series circuits in the organ unless we have to put like two light bulbs in series to make them dim, and one shows through the name board and the other is covered over with black tape so you don't know it's there. In parallel circuits, there's one just there. Each load is connected with its own circuit. Common sense tells us, in this case, the current will double, which is okay, but you can work through the math. Next. The total resistance of a circuit can be determined by dividing one divided by the resistance of the one load plus 1 divided by the resistance of the second load. So here we have two 40 ohm loads in parallel. Substituting numbers into the formula, we get this, then this, and that. The total resistance is 20 ohms, which of course you knew intuitively because you've got two 40 ohm loads together. Is it too early? Is that clear? Okay. But rules of parallel circuits. The first rule, the total resistance of a parallel circuit is always less than or approximately equal to the smallest resistive branch. So in that former slide where we had two loads, let's say one was 40 ohms and the other was 4,000 ohms. The combined current draw of both of them from the power supply would be a little less than 40 ohm by itself. So this formula that was just up there is useful when you're figuring out the resistance of the total resistance of different resistors. The voltage is the same across all branches of the parallel circuit. Well, clearly you have a plus and a minus and a bunch of crap going between them. The total current is equal to the sum of the individual branches. Series circuits, there we are very rare in organ building, so we'll skip the detail. In a series circuit, the loads are connected end to end so that the total resistance is the sum of the individual resistances. However, Ohm's law dictates that because the resistance in the circuit has risen, the current has fallen, so the force in the magnet will be reduced. This is why we don't use series circuits. Unless, of course, you have, say, a 24-volt organ and you have only 12-volt magnets in your kit. You could hook two in series. Each one would get 12 volts from the total of 24. Okay, everything has a resistance. What's the next slide look like? Okay, we can follow this. There are some tables in here and in the second handout, and I believe Bob has brought some stuff that allow us to look at the resistance per foot of various diameters of cable. So the power from the power supply, the power cable is 100 feet long, and so its resistance is 1 ohm. The cable from the load bus is 50 feet long, so its resistance is 0.5 ohms. How do we calculate the loss of voltage in the cable? Next. So the total resistance is 1 ohm for the power cable, plus 40 ohms for the load, the magnet, plus a half volt for the ground cable. That's 41.5 ohms. If the voltage is 15 volts, next, Ohm's law again, current is equal to the voltage divided by the resistance, so you get 0.36 amp. Dividing 15 volts, which is the setting of the power supply, divided by 41.5, which is the total resistance. Iva Hooper would approve of this rewriting of Ohm's law that says voltage is the current times the resistance. And the voltage is 14.4. We lose 0.6 volts through the cable. This sort of exercise is worth remembering because quite often in an organ you'll find that all the voltages are fine until you push a general piston, and then it, Years ago I was asked to look at a Hildebrandt organ in New Haven, and they had a massive 150 amp Orgelectra in the attic. It was so impressive it had an eye hook on the top for craning it in. The organ was a big 3-manual tracker with lots of current-hungry slider solenoids. And if you pushed divisional pistons, it was sort of okay. When you pushed a general piston, it just barely, and I can relate to what that feels like. So I went up to the attic and asked whoever was at the console just to go push a general on which everything was set and go between it and cancel. And I went up there and I looked at the power supply and I read the voltage and it was going, not much change. Then I looked at the cable that ran down to the organ. It was a piece of Romax. And I felt it. And I shouted, "Stop!" because it was getting hot. And obviously, Mr. Hildebrand hadn't seen this. Okay, in the series circuit, where you have the power going through one element and then another and then back, the total resistance is calculated by the formula using 20 loads of 40 ohms. So again, you can use this formula next, but this gets kind of stupid. Yeah. Okay. In the organ, we are faced with practical decisions of how large should the power supply be, how big should the cable be, how long should the cable be, and generally we use Ohm's law to figure out how much current each magnet is going to consume. And because in the organ there's never one of anything, except maybe a blower, you add up, you do the sum of all the current that the action magnets are going to take. I'll get to this in the next section. But just as we don't provide blowers to blow every pipe in the organ at the same time, we don't generally provide power supplies that can run every magnet in the organ at the same time. So you need some sort of seat-of-the-pants guesstimation. I just say, well, I don't remember what I say. It's in the next part of the lecture. Stay tuned. We'll get to that. Next. Is that it?
Yeah.
That's it?
That's it.
Oh, okay. Very good. Well, that was fun. Power supplies. I've been asked to talk about power supplies. We might as well do that right now. The calculations that we've seen assume two things. They assume that the voltage from the power supply is constant and that the power supply has no resistance of its own in the circuit. That's part of the black magic that we don't need to know about, what goes on in power supplies. How many have worked with the small switching power supplies that folks are selling now? Yeah, unlike the Astrons or the big brute force Orgelectras, they don't break your toe when you drop them on your foot. But if you ever opened one up, there's a scary amount of electronics. And I'll tell you, I don't easily get scared by electronics, but those things are terrifying. Modern power supplies are usually regulated. This means they produce a constant voltage under varying loads. Older units do not, so as the load increases, the voltage reduces. This makes calculations more difficult. But for new systems installations where you have regulated power supplies, it's really not an issue in calculating the amount of current an organ will need. A regulated supply effectively has no resistance in the circuit, as its internal electronics compensate for changes. Do not, it says right here, do not try to measure the resistance with a meter, as it will not reveal anything and will probably smoke. I would never think to put an ohm meter across the terminals of a power supply. I kind of got smoke out of my system when I was a kid. I would build things and get my grandfather to plug them in the wall. 8 out of 10 times they'd go up in flames. But he was, I wish I could thank him. I mean, he was a very gentle and patient soul. Power supplies are normally rated by the DC output voltage and current. However, this current is almost always specified as fixed voltage, say 12 volts, or in the case of the power supplies we generally buy, it's 13.8 volts, which is the voltage at which you would charge a lead acid battery. Peter Piper picked a peck. The next term beyond Ohm's law, where we have volts and amps and ohms, is power. And that is simply the voltage times the current. In an example, if the power supply is 12 volts and it's supplying up to 55 amps, that power supply is rated at 660 watts. We're starting to see suppliers quoting their range of power supplies in watts. And, what's a watt anyway? You just divide it by the voltage and you'll get the current. These modern power supplies are current limited. This term means that when the maximum current output is reached, the internal controls will prevent the unit from being damaged because it simply lowers the voltage. And when the fault goes away, it's supposed to come back. Fusing is the simplest form of current limitation. Cheap and effective, it suffers from causing the load to fail until repaired. Fuses are often still fitted for ultimate failure protection, but rated higher than other systems, so they are used only as a final resort to avoid fire. Be sure to always replace fuses with the same value and type. Some fuses are designed to absorb surges, and if replaced with fast flow types, will fail again. If you look at an Astron, you'll find there's a fuse on the back. It's an AC fuse. It's in series with the line cord. It's the first thing the electricity encounters when it goes into that box. And after it, the next thing is the little cherry red light on the power switch that tells you it's on. Astron supplies are brute force. We'll draw some pictures here in a minute. And they have voltage regulating circuits that consist of pretty shiny transistors on the side of the big ugly heat sinks that hurt your hands when you lift them. And those transistors, as we'll see later, act as valves. They control the amount of electricity coming out of the Astron. The fuse on the back is only there as a last-ditch effort to sort of preserve the good relationship you have with your liability insurance salesman by not burning down the church. Current trips, this is English, current trips are circuit breakers. Some systems have resettable circuit breakers, again requiring someone to reset them. Some circuit breakers will automatically reset when the overload is removed, causing only a momentary failure. This can appear to be exaggerated by computer-based switching or memory systems, which take a few seconds to reboot after the voltage has gone away and come back. Current limiting uses internal circuits in the power supply to limit the current to the maximum available for that unit. Effectively, this circuit provides a constant power by reducing the voltage as required. Examples. Is anyone following along? Do you have this picture in your books? It's page 15. Yes, good, I see one. To increase the available current, more than one power supply needs to be added. Here, 2 units are running in parallel. There are lots of theories about the best way to do this. The best method depends on the installation and the type of equipment. However, there is one golden rule, it says here. Always join the negatives of the power supplies together with a large, very adequate ground bus. Where to connect the positive cables? Linking the 2 power supplies together with a short but thick wire is okay if either the 2 units are true current limiting types, like modern switching power supplies, which is the one that's pictured here. Each will contribute what it has to and not be affected by its neighbor. Or the 2 have output voltage tracking, such as the newer type Astrons that have a red binding post on the back panel, and it says to link them from one to another. That just lets the voltage regulators in each Astron talk to each other, but it's not foolproof. And why is it necessary to think about tracking between power supplies? Because if one unit has an output set fractionally higher than the other, all the current will flow from it to the load, and the second unit will do nothing until the load increases, so it draws more than the rated load from the first power supply, and then the first one will trip off, leaving the second one to take the load, which is too great, so it'll trip off. And that's not good. Next page. Another method is to distribute the power supplies to areas in the system where the load is fed in a current loop. I've never done this sort of thing. Maybe Bob, when he's talking about power, so he's shaking his head. No.
Don't do it.
Next page.
Don't do it.
What does happen typically in organs these days is instead of having one massive brick of a power supply doing the whole organ and being cabled everywhere, is to distribute power supplies throughout the organ. Typically, in the case of organs with slider motors that can each draw up to 3 amps, there'll be a bank of slider motors at a wind chest. There'll be some sort of solid state control to drive them, and then you can locate a power supply right there, which might provide 30, 35 amps, 75 in a really, really big division. And then you simply have the electrician. Not that anything is simple when dealing with electricians. Run outlets around the organ, and so you can plug your power supplies in, and when you turn on the organ, they all come to life. That has advantages that we'll talk about later in terms of voltage loss in the wire. But in the case of an instrument that has, where the organ and the console and everything is connected together, you will typically have one common negative terminal that runs through from power supply to power supply. So every voltage is referenced from the 0 going up. In this nasty example here, it does say one useful thing. The resistance of the power cable will help to soften the link between power supplies and provide for better load sharing. This system is similar in the way that power systems work for AC feeds in our homes. Well, not in our homes, but the guy who wrote this is English. And they have something called mains ring. Mains being the main power coming into your house. Goes into the circuit breaker panel, and it comes out of the circuit breaker, and it goes to the living room, the dining room, the playpen, and then it goes back to the same point in circuit breaker, so it forms a loop. The idea being, if someone hasn't tightened the screw on one of the electrical outlets, it can get fed from both ends. I tend to do much the same thing in organ wiring, where, for example, you have a rail of thumb pistons, and the common goes loop-de-loop-de-loop-de-loop-de-loop. You could just feed it from one end, but what happens if it breaks somewhere? Well, if you feed it from both ends, you'll never know it breaks the first time. I learned this early on with, I think it was a Wix organ that had a little braided wire connecting chopper to chopper to chopper. And of course, as you played, they all danced around. And eventually, no, it was a molar, sorry. One broke. And of course, that was fine, nothing happened. Then the second broke, but it was obvious, the keyboard was dead from tenor G to middle C. So you know right where to look. Series power supply circuits on the next page. Sometimes it's necessary to boost the DC voltage beyond what's available from the unit. Some manufacturers' power supplies can be connected in series to provide double the voltage. There's only one very important thing to watch for. Remember when we said that it's advisable to cut the negative link inside an Astron between the minus bolt and the chassis ground. When two units are connected in series, the negative terminal of the second unit is connected to the positive terminal of the first, and this makes it run at, say, 12 volts. There's a connection to the AC ground. If there's a connection to the AC ground, it will short out the first unit. Do not connect the AC ground from the device, as this is dangerous. Ask the manufacturer for advice. Well, I did that once. The first company I bought one of these switching power supplies from, I said, I put a test light on it between positive and the case ground, and it lit up just as if I'd put it on negative. And the sales guy said, oh yeah, they do that. There's a little printed circuit track inside that makes that link. All you need to do is put a wire between the positive terminal and the case. And a little bit puff of smoke will come out, and you'll be all set. Well, being no stranger to smoke, I went ahead and did that. And true enough, the case of the unit was no longer connected to negative. I once asked the folks at Astron why they do this, why they connect their negative to the chassis ground, and was told that it was necessary, it was a requirement of the Canadian telecommunications industry to which they provided power supplies. Okay, the next bit here on page 17 says, how much current does my power supply draw from the AC? Well, this is a very common question. If the friendly electrician may ask you, how many amps does the organ draw? Well, you look at the motor and you can give a reasonably good answer, but power supplies, especially ones that are rated in watts, well, this tells you how to do it. Power, as we said, power in watts is equal to the voltage in volts times the current in amps. The power through the power supply is constant except for one thing, efficiency. Some of the power is lost to heat. We normally assume that a power supply is about 80% efficient. I don't know if that's true or not, but it's a number. First, we calculate the maximum power coming out of the power supply. So if it's rated for 12 volts at 55 amps, that's 660 watts. We now allow for the handicap of its efficiency rating at 80%, and we increase that 660 watts that the power supply is going to deliver to the organ by the amount it's going to radiate as heat, and we come up with 825 watts, which is still not what the electrician wants to hear. So you divide 825 watts by 110 volts, and you say, sir, I need 7.5 amps, which is not necessarily the whole story. Have any of you encountered situations where when you switch on a power supply, it runs, and then the fuse blows or the circuit breaker trips? Yes, yes. So don't tell him 77.5 amps, ever. Tell him 20. He'll understand 20. But it can still happen, and that is because depending on the type of power supply, there can be a large inrush of current. And I remember first hearing it on an Astron when I switched it on. All the metal parts went,
Mm-hmm.
and I went, oh. But it was working, so I forgot about it. Many years ago, when the big Fisk-Rosales organ was installed at Rice University, it has distributed Astrons all over the place. It's a huge organ, and there was like half of a column in the circuit breaker panel was circuit breakers for each power supply. I had specified a separate circuit for each Astron, thinking, oh, this is going to be really safe. Every time you turned on the organ, there was clickety-click going on in the next room as some of the circuit breakers tripped. And you'd have to go there and switch them on, and then life was good until you did it again. So I looked into it, and it turns out that there are certain devices, like these Astrons, which, when you switch them on, you have to charge up the big heavy iron transformer. It has to get magnetized. There are filter capacitors in there that are like winkers in a wind system that have to fill up. And to make matters worse, the way the slider control circuits work is that when you switch on the organ, all the slider motors go off, except any stops you may have on. And that's done intentionally so that if you're going through the organ and doing show and tell by saying, and this is the slider and this is what it does, if you leave any on, when you come back to the console and switch the organ on, which of course has all the stops retired because everyone does nice, tidy housekeeping, you switch it on, you want those solenoids to immediately reflect the state of the draw knobs at the console. But it does mean it's absolutely the worst case when you first switch on. The other place you'll encounter it is with these new switch mode power supplies, where there is a big inrush of current due to, I guess, all the black magic that goes on inside there. It's sort of, these supplies are kind of like the automotive industry in Detroit. I live near there, and trains are always going rushing by because they need to supply the just-in-time manufacturing system in these factories. The parts come in, and hours later, they're in a car and out the door. Well, these small, rather efficient power supplies are inexpensive and light, but they work on much the same just-in-time manufacturing principle as the automobile factories. They have a small transformer that runs at a high frequency that charges a capacitor, and eventually that current goes out to the organ. But it doesn't store it. It doesn't hold it in reserve. So it's very common for these power supplies, for some reason, maybe Bob can tell us, when you switch them on, even without a massive load connected to them, they can trip a breaker. So our friends at, I think it was Alan Bradley, said, oh yes, we make special circuit breakers for microwave ovens. Well, I don't have a microwave oven, but I have a similar problem. Well, then buy this circuit breaker. I forget what they're called.
High magnetic.
High magnetic. So circuit breakers tend to trip for two reasons. One, thermal. You've drawn just too much current. You've plugged in too many toasters. And before the wiring burns your house down, the circuit breaker will trip off. And the other is by magnetic surges. There's a coil in there that acts like an electromagnet. And if a surge of too much current goes through it, it'll trip the thing off. Any questions on any of this? Yes, Joe.
Dick, now that we have a few years of these switching power supplies in the system, so to speak, and you've installed lots of them, and each of us have probably installed a few of them here and there. Have you seen any problems that have been exhibited by them, or one company's is a little bit better than some other ones? Any issues with those power supplies? Or?
Oh, we'll all burn in hell eventually, Joe. if not for our choice of power supplies, then for other more fun things in our lives. I first encountered these, they're called switching power supplies or switch mode power supplies because basically there's a very fast electronic switch inside that delivers as much current as is needed to maintain the output voltage at the terminals. First time I encountered them was actually on a Fisk installation at the new concert hall in Yokohama. Most of the big organs in Japan have been imported by Yamaha, which seems strange, but the reason is that the clients that typically bought or buy organs in Japan aren't familiar with either the instrument or the process of importing. So Yamaha says, we'll handle it all, just write the check, which is very large. So anyway, when Yamaha imported this Fisk organ to Yokohama, and they said to Steve Deek, you know, we're getting kind of tired of having to depend on European suppliers for parts for their electronic control systems. Would you mind if we make our own system, which then we will service and be responsible for? Steve said, sure, as long as it doesn't cost any more than what we're used to providing. And so they said, we calculate. And they calculated and came back with a figure that Steve said was more than 3 times as much as what they would normally spend on their system of choice. They told the Japanese guy, and there was a pause. You could hear him gasping or blushing. He said, "Oh, okay, we do." So they did it for the same price. Anyway, they had 2 different kinds of power supplies in this organ. The ones that supplied the power for moving all the slider motors were big-ass brute force things in the bottom of the cabinet. A massive transformer, big diodes, a choke, all very, very reassuring. Much like we would have bought from OSI or Orgelectra or any other manufacturers in the 40s, 50s, 60s, 70s, 80s. But for the electronics portion of the system, they had these little switching mode power supplies. And I thought, oh, that's very cool. Maybe I can buy one somewhere. Anyway, the bloom came off the rose about 10 years later, and Steve Deek was there doing the annual maintenance on the organ, and this little man from Yamaha came through with a whole box of power supplies, and he started changing them all. So he said, well, they're working just fine. Why are you doing this? But will fail. And they said that their policy is to change them every 10 years. I thought, that was my gut feeling, of course. So I don't know, Joe. I use them where it's appropriate. Actually, I use them more and more because it's very convenient. And they're only like $150 or $250. And they come from a sort of a small range of suppliers. The one that's pictured in the handout is actually made by a company called IOTA, IOTA. And it's the one that's sold by Solid State Organ Systems with their label on it, and by OSI. I can't remember if OSI puts a label. I think they do. Yeah. So you know who to call in the first instance. But they're all basically the same thing under the hood.
There's a big difference in the last, 20 years ago they were horrible.
Mm-hmm.
And 10 years was an expected lifetime for those things. Today, parts are a lot better, and we know how to make them last a lot longer.
We've seen them burn out.
Yeah.
Yeah.
They still fail, but they should last a whole lot longer than 20 years ago. I wouldn't have put land.
You won't, well, you may burn in hell anyway, but still, not for that reason. You'll also see these little black wall warts, like there's one plugged in the wall right there. And it may be putting out 12 volts at an amp, which is, how many watts is that? Didn't think there was going to be a quiz, did you? It'll put out 120 watts, but it's pretty doggone small. And if you were to run it over the bandsaw, you would see that it's a switching power supply inside. The old ones used to be quite big and heavy, and they had transformers and rectifiers and chokes and stuff in there. Other questions on power supplies or anything else? Okay, pages 18 and 19 and 20 give some useful reference information on wire gauges and wire sizing. The one on page 19 is a useful little no-brainer chart. You look in the left column, how many amps are going to flow in the circuit. Let's say 15, and it's going to be 25 feet long. So you want to use a minimum of 12 gauge wire for that.
Page 19, what kind of voltage drop are they talking
I
about?
have no idea. I just copied the page. Of course, they're going to have to decide how much voltage drop is reasonable for this length of wire and this gauge of wire. Obviously, you could use welding cable and there'd be no voltage drop, but you wouldn't stay in business very long. Typically, in AC house wiring, it's done this way. That's a 20 amp circuit there. So it will require, I believe, 12 gauge wire to the circuit breaker. But you don't know how far the circuit breaker is away. So it's still, this is kind of a coarse estimate, but at least it should keep you out of the very deep water.
Dick, in my presentation, there's a link to a great online calculator. You can stuff in your, what you want the voltage drop percentage-wise, so on and so forth, and it will give you whatever you know down to hundredths of a foot. So,
That's really wonderful,
yeah.
and I'll take notes. Yeah.
Question, say you're wiring up a Friday afternoon and you don't have 10 gauge and you've got some smaller wires, is it appropriate to put a couple of wires using the formulas that you gave earlier?
Oh, sure, absolutely. If you have only a spool of 26 gauge wire, wad them up. Yes, absolutely. And I think in a class once I was told that the electrons tend to flow. It's called the skin effect. Skin effect? No, it's nothing dirty, guys, really, truly. That the electrons tend to move along the outside of the wire. And so there actually may be an advantage to use, say, 3 number 14 wires instead of 1 number 10. These are just off the cuff tough numbers. Ryan.
I'm currently rewiring an instrument where the original builder had used undersized wire and then, well, first he wired the organ with solid wire, which we all know is a huge mistake and you're not supposed to do that. And then but once he realized the organ wasn't working right, he came back and added some stranded wire over top of it to each of the relay stations, and then the organ was fine. But in my rewiring of the instrument, I didn't want to maintain that solid wire. I ripped it out, but I didn't want to have to replace the stranded wire that was there, trying to save a few dollars. I wanted to know, could I just add some wire to it? So I did this exact same piece of research, and what I found was that, for instance, the amount of current that I needed going to each switching station, I needed number 10 wire, but there was number 12 already running to it. So should I rip it out and put in number 10, or could I just simply add another set of number 12s? And what I found was that adding another number 12 to the 12 that was there gave me the equivalent of number 9 wire.
Right. Which is a good thing.
Yeah.
And that's what you did.
Yes.
Ryan, I know Ryan quite well. He is compulsive, like the best of us, but he's also practical. And yeah, that's the perfectly appropriate thing to do. My colleague Vladimir would not do that. He'd must take out, put in new wire. He's been known to rip out wires because they're the wrong color.
Well, that's...
Well, now that, yes, he's also been known to hook things up assuming the colors are right and the smoke comes out. Anything else? There'll be ample opportunity. Okay, the last page here is this little wheel that shows the various permutations of Ohm's law. if you know any two of the three items, you can solve for the third one. The teachers always used to say, and you'll solve the equation by, and I never say that. It's like, you know, we all suffered through things our parents said. I'll never say that to my kids, but out it comes. I even talk to my cats that way. Okay, so the next bit here is this thing that we do every year at the AIO exam review session, and it's keyed to some incredibly, oh, there's a wheel again, look at that. It's keyed to this very old handout that I've been so lazy all these years I've been doing it. I haven't updated it, but most of what it says is true, and if I say anything or it says anything that's false, just, you'll be very quiet. So, it says here, the purpose of today's session is to review the basic principles of electricity and its application to organ building with a view to preparing for the examination. The exam has been written by organ builders who are aware of those areas of electrical engineering and calculation that bear directly on our day-to-day activities. This isn't a crash course in rocket science. Oh dear. It's just a review of the essentials of electricity, what it is, what the basic building blocks of electrical circuits are, and how to specify and use them in the organ. We'll look at power supplies, current flow, magnets, resistors, and semiconductors. We'll even brush up on which end of a diode to shake hands with. It's practically impossible to build even the simplest organ without knowing something about electricity, if only how to wire up the blower. Servicing organs can expose us to a mix of technologies, sometimes a very intimidating and complex mix. Most of us are less comfortable with electrical systems than we are with mechanical systems. After all, it's easier to understand something if you can see it move. None of us would be in this room if we didn't have some mechanical ability and curiosity, coupled with a musical sense and the need for creative expression. It's just that mix. You're grinning. Oh, he's so expressive. What? It's just this mix of things that makes organ building so much fun. You can't see electricity, only the evidence of its presence. A glowing light bulb, a moving magnet, or perhaps dark gray smoke. Blowers whiz round, rectifiers rectify, whatever that is, and Lord only knows what goes on inside a transistor. Maybe we'll... I brought one here, and if there's a can opener later on, we can pry it open and see what goes on inside. And what is solid state anyway? I've sort of always preferred things in liquid state. But a semiconductor? Yeah, surely that's an oxymoron. Since we can't easily visualize current flowing through a wire, it's often helpful to make an analogy to a plumbing system or a winding system. The principles are nearly identical. Although old Ben Franklin found electricity up in the sky, he hadn't a clue to what it actually was, but he knew he could snag it in a storm, produce it in a battery, trap it and store it in a Leyden jar, and let it out when he wanted to. Whatever it was, it went from somewhere to somewhere, traveling through a metallic wire, or your body. Fortunately, Ben, and in fact, inventors as recent as Edison, didn't need to know what electricity was in order to use it. They worked out the rules empirically and found ways to apply them. I live not far from Greenfield Village in Dearborn, Michigan, where Henry Ford brought very interesting buildings from around the world, including Edison's laboratory. And it's a fascinating place. I was told on a tour there that Edison had certain goals for the laboratory. They had to produce a minor invention every 10 days and a major invention every 6 months. It kind of takes the romance out of it. When I was a kid, I wore out sections of my mom's Compton's encyclopedia, the sections that dealt with radio, electricity, telephones, and the organ. These books were published in the 1920s, when the Industrial Revolution had already changed the face of the world. The photographs were fantastic, and the constant theme was the wonder of science and how technology, most often electricity, was changing the world. It was that same runaway exuberance in the encyclopedia that produced some of the greatest triumphs of the period and some of the greatest monstrosities. Incidentally, the cutaway view of the pipe organ in this encyclopedia was a tubular instrument. It was in a photo in the Vermont section and showed an organ on the erecting room floor of the Esty Company in Brattleboro. The console was here. It had huge bundles of lead tubing going into the organ, and you saw sort of a cross-sectional view of pipes. I thought, wow, I can understand this. You push the key, the air goes in the tube, and it comes out in the pipe. I'm going to be an organ builder. Well, getting back to the example of the parallel between electricity and plumbing, a battery can be likened to a water pump. Water goes in one end and gets pushed out the other, making a complete circuit if the water goes back to the intake. Ben Franklin knew that electricity acted in much the same way. It wanted to get from one terminal of a battery to the other. He reasoned that there was an abundance of electricity at the former and an absence at the latter. So he called the one positive and the other negative, assuming that electricity, whatever it was, flowed from the abundant positive to the depleted negative. It was only, this dates it. What's typed here is it was only in this century, I've changed, it was only in the last century, with exploration into the atomic structure of matter, that we've discovered that electricity actually consists of the flow of negatively charged electrons, and that it's these negative charges that build up at the negative pole of a battery and want to get to the positive pole, because, as we all know, opposites attract. So, with all the best intentions, Ben got it wrong. As a testament to the fact that you don't really need to know what you're doing in order to do it, we still refer to electricity as flowing from plus to minus. It's sort of a nod to the last century, even though we now know that the electrons are actually going the other way around. We call this positive to negative flow conventional current. So, now I have to decide which color to use. I never understood in school how uncomfortable it was for the teacher to write on the chalkboard, and why this one teacher always went downhill. You know, she'd run out of space and then she'd go over here. Now I know, and I'm really, really bad at it. So, we say the battery is a pump. The symbol for the battery is this. And this is the positive terminal, and this is the negative terminal. This, of course, is one of the great inconsistencies in life, because, as we all know, a flashlight battery looks like this. So the short bit is the plus, and the long bit is the minus. But in the schematic, it's the opposite. Maybe they were thinking about the electrons. It is a great inconsistency in life that the symbol should be just opposite what a battery looks like. This was actually the second clue I had in life that I would never understand the universe. The first was seeing an ice-making machine that worked on the absorption principle. My dad showed me this big box that had a gas burner in the bottom with beautiful flame. And then he closed that door and opened up the top, and it was spitting out ice cubes. You know, this is just wrong. We all know this is wrong. Okay, completing our plumbing analogy, a conducting wire. I think I have to, Is this the eraser?
No, it's up on the.
Thank you. Big plan for everything here.
Except for that.
Except for that. It's okay, I knocked it down yesterday. So let's draw our battery down here. And we'll go up here and we'll put in a light bulb. And just to be fancy, we'll put a switch there. Okay. So this is minus and this is plus. What's happening is the battery is pumping out electricity to the filament in the light bulb. Through the switch, it lights with the glass around the light bulb, and it goes back into the battery at the negative terminal. This is what's called a complete circuit. You don't need to see it anyway. If this were a plumbing example, a pump might be pushing water up a pipe through a valve, causing, say, a paddle wheel to rotate in a water motor, or maybe that little kid in the fountain peeing in the bowl, and then the water comes back and gets sucked into the inlet of the pump, only to repeat the cycle. In the electric, just as the same molecules of water go round and round through the pump, the same electrons go round and round through the battery. If you're designing plumbing systems, it's necessary to quantify what's happening in order to know how much water is needed and how big the pipes need to be to get it there. Any of us who've been in the shower when someone flushes the toilet will know that this is important. In plumbing, pressure is usually measured in pounds per square inch and flow in cubic feet per meters, or gallons per minute if you have a really big shower. The corresponding terms in electrical measurements are volts for pressure, amps for flow. Volts and amps. The relationship of volts to amps in a circuit is defined by Ohm's law. I don't have to write it out, do I? Oh, good. It's in your books. The relationship is defined by Ohm's law. The terms were named for the modest and very good folk who invented them. Mr. Ohm and Mr. Volta worked out that in a circuit like this, if the battery has a pressure, or in electrical terms, a potential of 1 volt, and it pushes the electricity through a wire through a resistance of, let's say, 1 ohm. The Greek letter omega is used for ohm. The flow would be 1 amp. 1 volt through 1 ohm equals 1 amp. The math can't get any simpler than that. For some reason, the symbol for, generally you'll see Ohm's law written E equals I R. And what's E? I've got a V there. The E stands, I think, for electromotive force, and the I stands for amps, current flow. Thank God, R stands for resistance. The one friendly thing in all of this. Resistance is simply the resistance to the flow of electricity. I know it's not kosher to define something by itself, but I don't know how to explain it. Maybe we should go back to the plumbing example of that garden hose up here. If you stomp on it, you're providing resistance to the flow of electricity, or if you tie it in a knot. There are only these 2 electrical laws we need to know in organ building. Ohm's law and so what use is Ohm's law? Well, how do you figure out how big the rectifier in an organ needs to be? We already touched on this. You need to know how much electricity the magnets consume. Fortunately, it's very simple. Instead of a light bulb, let's draw an electromagnet. The loops represent hundreds of turns of fine wire on the magnet coil. If we were to draw it properly, we'd include something here to represent the soft iron core, so as not to imply that the coil is being wound on a soda straw or a swizzle stick or a dowel. Organ Supply kindly stamps resistance in ohms on the coils of their magnets. Just to make the math easy, let's call this one 100 ohms. And let's say the battery supplies a pressure of 10 volts. How much current is going to be consumed by the magnet? What's the rate of flow of current in the circuit? It's determined by the resistance of the magnet and the voltage of the power supply. If we were to make a short circuit here, like that, the battery would pump out all the current it could, limited only by the resistance of the wire, the poor failing switch, and the internal resistance of the battery. But the magnet coil is limiting the current to a sensible amount because it has resistance. So how much current? It's pretty easy with these numbers. And the current is equal to the voltage divided by the current or 10 volts divided by 100 ohms, or 0.1 amp. So this one magnet here will consume 1/10 of an amp of current at 10 volts. If you make 100 of these guys work at once, your battery will need to deliver 10 amps without collapsing. So to work out how much current is needed for the playing action of an organ, you just figure out how much current each magnet needs and multiply that by the maximum number of magnets you might expect to be played at the same time. A sensible number, of course. At some point, you're going to have to decide how much electricity to provide. I use that rule of thumb I mentioned that doesn't often get me into trouble, based on playing 10 notes on the manual, on a keyboard with all the divisions coupled. If there are sub and or super couplers, I add another 50%. And that's just for the, plus a couple notes in the pedal with the couplers and a couple of pedal notes in its own division. And that's just for the playing action. If the same rectifier supplies the combination action, you need to add another, say, ½ amp per draw knob or stop tablet. And you have to assume that someone might just play that big chord while pressing a piston. And don't forget the stop action magnets, many of which are going to be on. So add all that stuff up and then choose the next larger rectifier. Years ago, my friend Nicholas Kinston talked about the dedication he played of a large Kleist organ in Germany. You've probably all seen the picture. It's the one with many, many ranks of chamads and a big clock face that is made of cloth, and the swell organ is behind it. Anyway, Kinston was asked on short notice to come and do the dedication on this organ. So he came, and it was one of these busy basilica monastery sort of places, so he's practicing at night. And he had a problem. The organ cut out. So the next morning, he phoned Kleist and said, is there a problem? And he said, there's a problem. He said, oh yeah? And they said they would send someone over to check it out. Nicholas went home and he smoked and he slept and he smoked. He smoked a lot, by the way. He told me he thinks American smokers are becoming more and more healthy because of all the fresh air they're forced to inhale, smoking outside. So he came the next night, and same thing happened. And he said, excuse me, I guess you didn't get a chance to, oh no, yeah, it's okay. No, it's not okay. Okay. So they said, well, we will come tomorrow with the representative of the manufacturer, Weiss, and our people, and you will show us what is wrong. Okay, so Nicholas puts the music up in the rack, and he's playing along, and pushes the button. Oh, see? Oh, but you cannot do that. What do you mean? You cannot play the organ while you push the button. It's verboten. Okay. So, you do have to allow for crazy organists like that. If instead of chest magnets for the stop action on, well, something of that ilk, you have slider solenoids that have a resistance of 5 ohms each and intend to run them on, say, 14 volts, the amount of current used by each solenoid will be 12.8 amps. An organ of 25 stops might therefore require a whopping 70 amps to move the stops. This is, of course, why E.M. Skinner didn't build slider chests. Can you just imagine the generator? So, now we know all about batteries, light bulbs, electromagnets, and resistors. Well, resistors look... It is going to fall, you know. This is the schematic symbol.
Is there more resistance on the right than the left?
I'm afraid so. And in fact, I have one right here. You can play with that. I was trying to find a variable resistor for the next demonstration, and I found some that had very heavy wire here and very light wire here, and I did think, oh, that's a lot like my drawings. So, that's the symbol for a fixed resistor. Resistors come in 2 forms generally, fixed and variable, like the one I was just holding. The symbol for a variable resistor is very much the same. So, like that. So it might be a sliding resistor that you move a clamp along to change the resistance. Fixed resistors consist of some terms of nichrome wire or resistance wire. It's wire that doesn't conduct electricity particularly well. Or, as in the fabulous old radios I used to take apart with wires as a kid. This is sort of my sins of a misspent youth. There was a guy across the alley who had a ton of old radios, and he gave them to me. And I thought, oh, parts! And I diked everything off and put them in little cans. Those resistors simply consisted of a block of carbon with wires tightly wound on each end and then painted. Nowadays, they're all very sanitized. The carbon lives inside a ceramic container. The leads come out tidally from both ends, and it's painted festive colors, which I'm told means something. Let's go for a practical example. We'll get rid of all this rubbish. And we'll reinstate our light bulb here. Let's say you want to put a resistor in series with a Sforzando lamp on the console to limit its brightness and extend its life. You could insert a variable resistor right here. That's an arrow. And adjust it until the light becomes the perfect brightness, sort of like adjusting the chandelier in your dining room. So you take out your variable resistor and you measure it with your Radio Shack ohm meter, and then you go to the electronics store where you confidently announce that you want one 200 ohm resistor, please. The clerk will ask you, how many watts, sir? What? What? It's sort of like who's on first. You explain that you just want to make a light bulb dimmer. Then the clerk lights up and suggests, you want one of these solid-state dimmers and just put it in the wall where the... No. It's in a pipe organ. Oh, they still make those things? Well, he said he thought he heard one at a ballpark somewhere, but he doesn't. Well, we've all been in that movie often enough, so you just plow on and shamelessly ask, well, what's a watt? Well, sir, the acne-faced youth says, it's a measure of how much power will be consumed by the resistor and dissipated as heat. Blank-faced, your eyes begin to glaze over. So he draws you a little picture and scribbles in some numbers. Right. Here's the same picture. 12 volts for the battery, 200 ohms for the resistor. Right. So how big is this light bulb, sir? Oh, it's a metric or no. How much current does it take? Well, I don't know, but it says 12V60MA on it. Fabulous. The guy's off and running. Knowing Ohm's law, he works it out. What's the light bulb's resistance? By Ohm's law, he calculates that it's 200 ohms. This is all a put-up deal, and Bob should be shaking his head by saying light bulbs don't have a constant resistance. It varies whether how hot they are. So you've got a 200 ohm light bulb here. 200 ohm resistor here. So he does the Ohm's law calculation for this circuit and determines that the current flowing is 0.03 amp. A little more scribbling and he announces, you need a 1/4 watt resistor, sir, and here it is. You go back to the church and you solder it into place and no one notices or is particularly impressed by the soft red glow. But you doze off to sleep that afternoon or evening. And you think thoughts of 100-year-old Sforzando light bulb. It's beautiful. But how did the kid work it out? How did he know you needed a 1/4 watt resistor, and what is a watt anyway? Here we need to introduce the second important equation, which gives us another letter, W, for power, which is measured in watts. I understand that Mr. Watt had something to do with steam engines a long time ago. Anyway, the symbol W for watts is equal to the volts, which is E, times the amps, which is I. It can also be written as W equals I squared R. You get that equation, as Ms. Hooper would explain to you, by substituting Ohm's law in here. It's true, I guarantee it. So how did he figure out how power the resistor had to waste in order to make the light bulb glow just like it did with your 200 ohm resistor? He multiplied the current, which he determined from Ohm's law was 0.03 amp by itself, and multiplied that by the resistance 200 and came up with 0.18 watt. A 1/4 watt resistor would be adequate. It could dissipate a 1/4 watt of power as heat without becoming toast. We said that one way of making a resistor was to wind a resistance wire around a soda straw. Well, if we didn't, we should have. The resistance wire that's used in making resistance is a rather poor conductor because it has more than the average amount of resistance. All wire has resistance, at least at temperatures above absolute zero. Table 2 in the conveniently unnumbered pages here. No, further. Keep going, Peter. Or, it's a table, it's got lots of numbers. Yeah. Past all that rubbish. Rubbish. Past all those words. They're just words. Go on. Find the table. That, okay. Peter will catch up. Aaron has the tables. Yep. Table 2 in the handout shows the resistance per foot of wire of various gauges. Huh? Okay. For convenience, it also shows the total resistance for a given length of wire. You'll note that 100 feet of the smallest gauge shown, which is 28 gauge, has a resistance of 6.5 ohms. That's a significant amount of resistance. So instead of embarrassing yourself at the electronics store, you could have just added about 3,000 feet of 28 gauge wire and had the same effect. Plus you'd have, lots of spare wire there for next time. In the earliest days of electric action, current was supplied by batteries and later by generators. 8 or 9 volts was enough for those early electromagnets, and you might need a whopping 10 amps for a really big organ. Feed and ground wires didn't need to be very large at all. Connecting ground wires under washers with wood screws usually didn't give much trouble, as the magnets could tolerate a drop of several volts and still work. But these days things are a bit different. Turning back to our earlier example of 25 slider motors drawing 70 amps, after having figured out how large the rectifier needs to be, the next thing to determine is how big the wire needs to be between the rectifier and the slider solenoids. While losing electricity in a wire on the way to the Sforz lamp might be desirable, losing it on the way to these big solenoids certainly isn't. After all, you've paid big bucks from the solenoids, and you need power. First of all, you have to decide how much voltage you're prepared to lose. This is what Bob was referring to. How much voltage you're prepared to lose between the rectifier and the solenoids. It's a trade-off, like everything else in organ building, between size and money and lost volts. The bigger the wire, the more expensive, the less voltage lost, the smaller, well, you get it. So you say to yourself, well, shucks, the power supply is 14 volts. 13 volts is almost the same. We can afford to lose a volt in the wire. And it's only going to be that bad when all the stops move at the same time. So if they turn out to be a bit sluggish, we'll just crank up the rectifier a notch. So what the heck. But remember, those solenoids are controlled by solid-state relays, which, as we'll see later, lose 1/2 volt going through them. So to maintain a minimum of 13 volts at the solenoid, you can afford to lose only 1/2 volt in the cable. Okay, so you look at table 1, resistance, well, you know what it says. And you find 0.5 volt drop in the left column. The wire is going to be carrying 70 amps. So you go across and the table tells you that the wire can have a resistance of no more than 0.0072 ohms. Now you turn back to table 2. The solenoids are 50 feet from the rectifier. So how long is the wire? How long is the wire? Oh, guys. Remember that there are 2 wires. There's a positive going to the solenoids and a negative coming back. So you need to double the length. You can't allow more than 0.0072 ohms. So you look down the 100-foot column until you come to 0.00642 ohms. The column at the left tells you you'll need to use 3/0 gauge wire. That's welding cable. Shit. This is when you decide to move the rectifier a whole lot closer to the solenoids, and you work out the math for 25 feet. You go through the same exercise, and it comes out to be number 4 gauge wire. That you can afford. And as I mentioned earlier, many builders are locating the power supplies very close to these heavy loads. In the console for the combination action, moving electric draw knobs or stop keys. In the organ, moving big banks of slider solenoids. It minimizes the voltage drop in the wire. And another technique that's being used more and more in this country, and it's very common in Europe, is to run the organ on 24 volts. Because if you remember Ohm's law, if you double the voltage, the current is reduced by half. If the current is reduced by half, you can use much smaller wires and still maintain the same voltage drop. So in any of these circuits, well, like that one, we could look at the power being dissipated by the light bulb or the solenoids, by the wire, knowing the resistance of the wire and the resistance of the solenoids. If we're really anal, we could work out the voltage drops everywhere and see how much power is going to the solenoids and how much is being wasted in the wire. Where do these watts go? The organist pushes a piston, the rectifier hums, the electric meter spins, but what happens to the energy? Well, it comes out as heat. These are the same watts that describe a toaster's toasting capacity, or how much heat you get from your landlord when playing the stereo too loud. Slider solenoids from Heuss or Laukoff are designed to have 100% duty cycle. Oh, that looks good. Which means that you could have them on constantly, and they probably wouldn't catch the church on fire and ruin the friendly relationship you have with your insurance salesman. They will, however, get warm and maybe hot. It's the watts coming up. Questions about power and heat and fire and flame? So far in these circuits we've drawn, you could turn the battery around the other way. In old organs, in the good old days, before any of us knew the diode word, it didn't matter which way round you connected the generator. In fact, in the early days of chest magnets, the iron wasn't particularly good and tended to get magnetized after a while, which could cause notes to stick on. You'd play a note, the magnet would go up, and even when you released the current, it would still hang there against the coil. This was called residual magnetism, and a typical solution was to reverse the polarity of the organ. Some places you'll still find big two-position knife switches that reverse the plus and minus. Really classy organs had a reversible mechanism so that every time the static bellows came up, the polarity would reverse. These switches want removing if you're putting any solid state in the organ. So, solid state. Well, we've got 11 minutes, that should do it. Diode. A diode is represented schematically like this. It's a one-way valve for electricity. Is there any, I was going to ask, is there anyone who doesn't know what a diode? That's too embarrassing. Does everyone know what diodes are? Come on. Oh, yeah. Thank you. That's the symbol, and physically it looks like this. Or the really old ones when I was a kid looked sort of bullet shaped like that. The arrow indicates the flow of electricity. It's conventional current. The current goes this way through the diode. The electrons go the other way, but we'll pretend we don't know. Diodes are very useful. You can do all sorts of cool things with them. They're also called rectifiers. In fact, they're properly called rectifiers. In organ building trade talk, we often call the power supply the organ rectifier. Well, it is, but if we're really technical about it, we should call them transformer rectifiers, which is actually a much more description of what they are. Back in the day, in the good old days, we used generators to produce DC, both in organs and in cars. Coils wound on an armature spun around within a magnetic field. Each coil was connected to a pair of copper strips at one end of the armature shaft, called a commutator, and there would be a dozen or so separate coils, each wired independently to opposite pieces of copper in the commutator. Carbon brushes touched the commutator in such a way that only the one coil of the armature that was producing voltage of the correct polarity at any one moment would get connected to the output of the generator. Any of you who have cleaned commutators, even in a dirty old blower room or on your vintage VW, will know that they're not very reliable. They get greasy and dirty, and the voltage goes down or goes away. This is why old consoles often had current lights, or even better voltmeters. It wasn't so that you knew the organ was on, the wind leaks pretty much took care of that, but it was so the organist could confidently come down on that first chord of the Wagner when the priest pronounces the happy couple, man and wife, and know that something would come out of the organ. What makes electricity in your car today? It's probably an alternator. An alternator is just a very, very simple generator with one coil on the armature connected to the outside world by slip rings. The alternator produces AC current, which looks like, you know, there ought to be a little button you press here and it just sets the... Okay, going back to the concept of 0 volts. If we make a graph of AC current like coming out of that wall outlet, it'll start at 0, it'll go up, it'll go down, then it'll reverse, and it'll go back up. Ad infinitum as long as you pay the electric bill. So, the alternator produces the same sort of thing. It's AC. Not much good for charging a battery. Disastrous, in fact. So we insert the diode. So let's pretend this is our alternator. And it's got 2 wires coming out. Let's put a diode here. And since we know how to draw a resistor, let's put it there. That could be all the electrical crap in your car or an organ or whatever. So what comes out, what goes in looks like this. What comes out looks like this. This is 0, this is positive, and what's happened is the diode has eliminated. Anyway, it works really great. It's kind of lumpy because you've thrown away half of the power coming out of the alternator. Well, if one diode is good, 4 must be even gooder. So we make a little bridge rectifier, and that's what it's called. And we start again up here. So we have an AC source that comes out, and at these 2 points, if you were to put an oscilloscope on it, which would draw a picture of the electricity, you'd see it's going positive, and then 0, and then negative, and then back to 0. So, our goal is to have here's our organ. The goal is so that this terminal is always plus, and this terminal is always minus. So bearing in mind that a diode is a one-way valve, we use it for steering here. Say, okay, at any one point in time, this terminal will be plus, so we want it to go there. Okay, so we put a diode there. Right, it goes through here. And of course, it wants to get to minus. It needs to get over to this one. So we put another diode, very sloppy diode here. So now for 1/2 of the cycle, going up, we have positive current going through a diode, through whatever it is, back up to the negative terminal, then through a diode, then back to the power supply, or whatever it is. At the next moment in time, instead of this being plus, this is plus. So we need to get from here to here. We put a diode here. It goes through the contraption. Needs to get up to here, so we put another diode here. Okay. It's called a bridge rectifier. Now electrons can march this way or that way, always coming out the same way in the end. The electricity coming out of this circuit will look like this. Basically, we've taken what previously was down here, and flipped it up top. It's very green, very economical. We're not wasting the electricity. In the organ, we usually don't hook up alternators to the blower motor. There's loads of alternating current coming in from the electric pole, but it's hot, 120 or 240 volts at least. It would certainly toast our poor magnets, so we transform it with a transformer, which looks like this. Iron core, wire coiled up around a bunch of iron, two windings, a primary with lots of turns connected to the high voltage, and a secondary with many fewer turns of heavier wire, producing, say, 15 volts. But it's still AC. It still comes out looking like this at that point. So, having already done the alternator trick, we're diode pros, and we know we can put in a bridge rectifier. And look, Ma, you got DC coming out. And it's plus here, it's minus here. If we put our meter on this, here and here, we will see that we're getting only 14 volts DC, but we know we put in 15 volts AC. Where did the extra volt go? Well, I'm afraid it's the ice maker again. Diodes don't follow Ohm's law. Great as it is, they don't pay any attention. Pretty much no matter how much current a diode carries, you lose about 1/2 volt going through it. That's why they're called semiconductors, because they don't behave properly. They're weird but useful, kind of like most of us. We'll break in just a minute. Diodes are made from silicon, which is the technical term for sand. But it's very special sand that's been doped to have either an excess of electrons called N-type silicon or a deficiency of electrons called P-type silicon. So if you were to do a cross-sectional view of a diode, it would look like that. This is N-type silicon, and this is P, and they're jammed together and coated with epoxy, so you tend not to pull them apart, or glass. Just to confuse you, the P-type silicon that is missing electrons, the N-type silicon has an abundance of electrons, the P a deficiency. Physicists will tell you that the P-type silicon has abundance of holes, or places for the electrons to nest. We know that electrons are flowing from the N to the P, but then we're told that the holes move from the P to the N, which has never made any sense to me. Fortunately, we don't have to be physicists to use a diode, or even to buy one. The Acme dude in the store will ask you only two questions: how many volts and how many amps? How many volts can the diode stand up to against the, how many volts can the diode stand up against? In the organ, it's the rectifier voltage, typically 15 or 24 volts. And how many amps does it need to carry? The little black jobbies that you buy from the trade suppliers are usually part number 1N4001. This isn't a sales promotion for diode. Well, it is actually. So that diode will block up to 50 volts, and it's part of a series, a family of diodes. 1N4004 will block 1,000 volts. So if you think of the diode as a little one-way flap valve, say a piece of leather in a nice plexiglass box covering a hole with the tube going in one end and out the other. You blow into the tube that shuts the leather flap, and eventually you're going to be able to blow hard enough that the leather will sort of get sucked into the hole and air will flow the wrong way. So that would be the breakdown voltage of the diode. How many volts, how much pressure can it withstand? Blowing the other way, the flap opens, and the current carrying capacity of the diode in amps or milliamps, thousandths of an amp, will be determined by how large that hole is and how big the tubing is and, the capacity of your lungs. I think we'll break right here, if we may.